All right, folks, here is problem 17.2 in the back of the chapter. It's on page 821. We were talking about this in class, but we actually never talked about what the final answers are, and they are not in the back of the book. So it's giving us an equation of ammonia and water making some ammonium and hydroxide. And it's really, we're looking at a base reaction here. We're creating a lot of OHs. Um, and the question is saying, well, if we have a concentration of ammonia as well as some concentration of ammonium, how many hydroxides are we going to have? But Dr. Hansen was saying, let's first examine it and say there is no hydroxides. And if there's no hydroxides, let's say there's no ammonium too. And let's see what, using the Kb values and the concentration of ammonia, what would we get? What would the number of hydroxides be? And I guess ammonium as well. So you have this equation here. It has our Kb value in it. It has our concentrations of both our two products up here at the top, and we're assuming it's water, so we don't have to include that on the bottom. We just have ammonia. So this is a fairly straightforward calculation to do. So we're just going to plug in. If we think about, here are our x's, right? So we're looking at an x there and an x there. We're multiplying it. We're dividing by our 0.164 molar solution that we have up there, and we're making it equal to 1.8 times 10 to the negative 5, which we get in the back of the book, which is our equilibrium constant for the space. So now it's a fairly straightforward problem to do. I'm going to multiply these two and get 2.95 times 10 to the negative 6th, and that is equal to x squared. And then I'm just going to take the square root of each of these, and find that x is equal to, so our concentrations of both our ammonium and hydroxides is going to be 1.72 times 10 to the negative 3rd. So maybe a little check would be good here. So what would a little check look like? Well, do these two x's, when you divide by your concentration of your ammonia, get to your 1.8. So let's see, is 1.8 times 10 to the negative 5 equal to our concentration of our ammonia, which is 1.72 times 10 to the negative 3rd times the same number, so I'm just going to square it. And I'm going to divide by our concentration of our ammonia, which is 0.164. Right. And I'm going to do the math on this. We do get 1.8 times 10 to the negative 5. So what does this tell us about our concentration? Well, remember, concentration also leads us to our pH or our pOH. So how do we figure out that? So I'm going to get rid of this purple. It's a little too thick for me here. So how do I do that? Well, I know my OHs. I also know that 1.0 times 10 to the negative 14 is equal to my concentration of my hydroniums, which I'm going to find out, because I like finding out how many hydroniums I have, as well as my hydroxides, which I already know. So now I can plug that number in, which is 1.72 times 10 to the negative 3rd. And I'm going to find out what my concentrations of my hydronium are when I go 1.0 times 10 to the negative 14 divided by 1.72 times 10 to the negative 3rd. And my hydronium ion concentration ends up being something around, what is my hydronium concentration? End up being something around 5.8 times 10 to the negative 12. Right? So pretty, in comparison, pretty small number. A lot more hydroxides compared to my hydroniums. So this tells me that my pH is going to fall into the basic scale. And remember, when I do pH, I'm going to use my hydroniums. So I'm going to do find the pH. I'm going to do, let's do a different color here. Let's go the negative log of this concentration of 5.8 times 10 to the negative 12. And it's going to tell me that my pH is equal to 11.2, which is a fairly basic solution. And I know that pH and pOH go hand in hand, so I'm going to just subtract. I'm going to subtract 14 minus 11.2 to get a number of about 2.76. But a check would be, let's take our concentration of hydroxides and take a negative log of that, and that would be the same number, 2.76. So what this is showing us is the concentrations of hydroxides and the pH of a solution without any of our product. Well, the question isn't asking that. It's asking about, well, what happens if we put some product in? And what happens if we put some product, ammonium, with some chlorides as well? What's the concentration of chlorides? Well, the concentration of chlorides are going to be the same concentration because of the one-to-one relationship with the ammonium. So Cl minus should be 0.102 big M as well. So I'll write these down as our final answers in a second. But let's do the calculations on this one. So what are the calculations on this one? What are they really going to look like? So let's take our, we'll take a look at our ice table. Well, our concentration of our ammonia is going to go down by a value of X, but the number is going to be really small. And why is the number going to be really small? Because when we take a look at our number here, when there was no ammonium in the solution, 1.7 times 10 to the negative third. So if we already have some ammonium in solution, we're going to get even fewer hydroxides. So this is a fairly large concentration, just as our ammonium is. So we're really going to have to use the assumption here. So we're going to assume that this number, this concentration, isn't really going to go down by a lot. And we're also going to assume that this concentration of ammonium isn't going to go up by a lot. But we do want to find out what our concentration of hydroxides are. So I'm going to, in a very similar manner to what I did in the previous one, I'm going to plug in some Kb values. So I know my Kb is equal to my concentration of my ammonium times my concentration of my hydroxides, all divided by my product, or my reactant, in this case is NH3, my ammonia. All right, so now let's plug in some numbers. And I'm only going to miss one number here. And the number that I'm going to miss is the exact number I'm looking for, which is my hydroxide. So 1.8 times 10 to the negative fifth is equal to, I already have my concentration there, so I'm going to plug that in at 0.102 big M. I'm going to multiply it by X because my hydroxide is definitely going up since I start with 0. And I'm going to divide it by the given of 0.164 big M. The math on this one is fairly straightforward. I'm going to multiply by my Kb value and my concentration of ammonia, and then I'm going to divide by 0.102 to get an X of 2.89 times 10 to the negative fifth. Sorry, I'm squeezing that in a little bit. And what is my X? My X is equal to my concentration of my hydroxides. All right, so now I've got my concentration of hydroxides. Well, just like I did in the last one, I like to, if I have hydroxide concentrations, I also like to figure out my hydronium concentrations because I do have both of those in solution. And if we take a look at how many hydroxides I have here, 10 to the negative fifth, compared to what I had here, 10 to the negative third, you can see that we went down, this number of hydroxides went down, so I'm going to get closer to neutral. So that 11.2 number that I found for pH should get closer to 7. Let's see if that's the case here. My hydroniums should also go up as well. All right, so how do I do the hydroniums? Well, again, I know that 1.0 times 10 to the negative 14 is our number of our concentration of our hydroniums times our hydroxides. Now I do have a number for hydroxide, which is 2.89 times 10 to the negative fifth. don't know my hydroniums, and that's what I'm looking for. But I do know that everything, or the product of those two, is going to equal to 1.0 times 10 to the negative 14. And finally, when I do the math on this, it's not too hard. I'm going to get my hydroniums concentration is equal to, what was my math on this one? Is 3.46 times 10 to the negative 10. 10 to the negative 10. So that's how many hydroniums I have. Well, over here, I had it to the negative 12th, so I know my hydroniums went up as well, which makes sense. If my hydroxides are going down, my hydroniums should be going up. So again, I'm just going to take I'll do this one over here finally. I'll go the negative log of my hydroniums, which is 3.46 times 10 to the negative 10th now. And that's going to give me a pH of 9.46. I'm going to subtract 14 to get my POH. Or I could do the negative log of my hydroxide here, 2.89 times 10 to the negative 5th, and I should get the same number when I put it in my calculator, 4.54. All right, so what do we get? Well, our hydroxide numbers should be around 2.89, depending on rounding, times 10 to the negative 5th. That's the key right there, 10 to the negative 5th. My ammonium concentration is going to be exactly as was given, 102. Oh, by the way, this is concentration, molarity. 102 big M, which is going to be identical to my concentration of my chloride, since it's a one-to-one relationship. Now my hydroxides, which I found right over here when I did my 1.0 times 10 to the negative 14 is equal to the product of my hydroniums hydroxides. I've got a 3.46 times 10 to the negative 10th. That's my concentration of those. So there are my answers for 17.2 on page 821.